Today we're going to look at linear and exponential functions. So let's take a look on the next page. We're going to complete the tables below, and then we're going to graph them. If you notice in the first table, we have our x and our y, our input and our output. And this function is f of n equals 2n. That means we're doubling everything, right? This is our input. If we plug it in right here, it's going to give us our output. So go ahead right now and fill the table in, and then we're going to graph it to the right. If you plug in a -2 times 2, you should get -4. -1 times -2 is -2. You should get 0, 2, 4, 6, and 8. Don't forget, this is like our input and our output. We have enough coordinate points there to graph it. -2, -4, -1, -2, 0, 0. And if you notice, this is making a line. All right, so we can connect these and it'll make a line just like that. Can you see the pattern? All right, now the next one's a little different. Next one down below, I'm gonna zoom in here. We still have our input of n. This is f of n, our output. But now if you notice, where is the variable? It's 2 to the n. It's up in the exponent, isn't it? All right, so if I plug in 2 to the n, that'd be 2 to the -2. We have a negative exponent, so don't forget we're going to move it. That would be the same thing as 1 over 2 squared, or 1/4. All right, you try it with the next one. 2 to the -1, that'd be 1 over 2. Next one's 2 to the 0. What's anything to the 0 power? It's 1. Fill in the rest of the table. All right, and then we're going to graph it to notice the difference. We're going to compare it to that line. So if I have -2 and 1/4, really tiny down there. -1, 1/2. At 0, it's 1. And then we have 1, 2. Look at that, they intersect. 2, 4, 3, 8, 4, all the way up here, 16. And if you kind of follow that, look at that trend. Woo, that is not the best line. All right, that is an example of exponential. All right. So number 2 asks to describe the change for each sequence when n increases by 1 for each. See, look, our x is increasing 1. Right? So our first function, for each input, the output is increasing by 2. For the exponential one, it's increasing by a factor of 2, so it's doubling. That's a big difference. All right, we're going to skip the next page and go to the top of 216. Here we go. Once again, we have a linear model compared to exponential. All right, this model is like our general equation, what it would look like. All right, so we have, if you look close on the linear model, isn't this y equals mx plus b? They've changed the variables because we're going to start looking at different functions, and we're going to compare them to an exponential function. So this is what you learned last year. We're just changing the variables. It's the same thing, and it's linear. All right, so just kind of keep that in mind. All right. Trying to get rid of that. Here we go. The meaning of A and B. So in this case, A is still our slope. A is the slope. B is our y-intercept. All right, here's an example right below it. Okay, so the rule for finding, oh, this is kind of interesting. Look at this. For finding f of x plus 1, wouldn't that be, oh, the next term, right? So this is our next output or term, right? All right, so what's happening each time? So for example, right here, if we start at, let's start right here. I'm going to make a table. X and y, but instead of calling it y, we're calling it f of x. All right? So if we start at 0, our intercept is 3. If I input 1, we're going to plug in 1 right here for x. What would we get? You should get 5. If I plug in 2, we're going to get 7. If our input's 3, we should get 9. Do you notice that it's increasing? By a positive 2 each time. It's increasing. It's adding, right? All right, now let's jump over to exponential model. All right, here we have an A. Oop, that's not much of an arrow. And a B also. That's kind of why they use those variables on our slope-intercept form, okay? So in this case, it's different. Our A is our starting value or our y-intercept, okay? It's where we start or the y-intercept. All right, it's like they're changing positions here almost, okay? And our B is our rate of change. What's another word for rate of change? It's slope if it's a line, right? Okay. So let's look at the example they have. They have f of x equals 3 times 2 to the x, all right? The 3 would be where it intersects the y-axis, our y-intercept, and 2 would be our rate of change. That goes along with the graph that we just did on the previous slide, right? It intersects at 3, and it's doubling. Each one is doubling. Actually, it kind of looks like the slide before. Doesn't actually go through at 3, though. See? Kind of similar. But that one would, the one we're currently working on might go up through 3. Okay. So let's go on back here. All right. Now, we already figured out what's happening, but let's do it again. So this is f. This is our f of x. All right, let's start at 0. And it says our y-intercept is, according to this one, dun, 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 our y-intercept is 3. All right. And then if I plug in 1, let's try it. Plug in 1 where the x is. 2 to the 1 power times 3, you should get 6. If I plug in 2, 2 to the power of 2 times 4 is 12. And last, plug in 3. 2 cubed times 3 should give you 24. All right, so if you notice what's happening on this one, oh, look at that. From here to here, what's happening? It's multiplying. By 2. So linear was adding 2. Exponential was multiplying by 2. So let's do a little sketch here. All right. So I have 0, 3, 1, 5, 2, 7, and 3, 9. Look at that. That lines up to be, oh, look at that. Kind of a nice line, huh? This one would be 0, 3, 1, 6, 2, 12, 3, whoa, 24, way up here. You're going to notice it's starting to curve and go up. All right, so that's the difference between linear and exponential. And if you notice, these are also increasing. They're going up, all right? If they were decay, we would have a negative slope for linear model, and our rate of change for exponential would be less than 1.